I'll take some time for introduction. Dear colleagues, dear friends, dear participants, it's my great pleasure to introduce our today's speaker, Xavier Waintal from CA Grenoble. CA stands for French Alternative Energies and Atomic Energy Commission. A few words about his scientific career. He obtained master's degree from Paris-Saclay in 1999 and then moved for 2-year postdoc position to Cornell University. After coming back to France, he obtained a permanent researcher position in Paris CEA. And then in 2009 moved to Grenoble to the center to this French Alternative Energies and Atomic Energy Commission, and he's currently working at the Quantum Photonics Electronics Engineering Laboratory, abbreviated as FELIX. He's leading researcher at the Theory Group. His research interests covering quantum nanoelectronics, spintronics, quantum strongly correlated systems. He has, and together with his group, has a long-standing commitment in development of very well-known open source software packages like Quant, T-Quant, and more recently also Tensor network package called Tensor for All. His today's talk is devoted to quantum computers versus classical computers and problems devoted to quantum chemistry, long-standing challenges in this research field. We are very excited to learn more, and please, Xavier, the floor is yours.
Thank you very much. Thanks a lot for the invitation. Very happy to talk to you guys. So maybe I should share my my screen. Where is it? Here it is. Okay, can you see the main screen? Perfect.
Yes.
Yeah, thanks a lot. I mean, I know it's very specific, I mean, difficult times for you, and I'm actually quite awed that you managed to continue on do physics and with what is happening in your country. So I'm very impressed. It's much easier on our side. So the title I want to tell you today is it's not going to be a very standard seminar. It's going to be a bit strange. So the title I put was like, which of quantum on classical computers is going to solve chemistry? What I really want to discuss is the problem of accuracy versus precision in chemistry. And I'm not at all a chemist. I don't know if there are some chemists in the room. If there are, you will quickly realize that I'm not a chemist. Nevertheless, chemistry is important for us, in particular for quantum computing, because it's really the application that has been put forward a lot as the central application for quantum computing. I'm going to look at one particular path, the most prominent one that has been put forward a lot, and discuss that. So the menu for today is the following. First, I want to discuss a bit what I mean by accuracy versus precision. So I want to state a bit what is it that you want to be able to do if you want to be able to say something relevant for chemistry, for solving all these applications that have been solved for quantum computing. So I will discuss this a bit. I will show you some examples of things that have been done with quantum computers, and I will try to convince you that it is not as impressive as people claim it is. Then I will discuss one particular algorithm. I only have time to discuss one. This variational quantum eigensolver, VQE, that is really the central algorithm that has been put forward and used to address chemistry problems on quantum computers. And if you want to understand how good an algorithm works, I mean a quantum algorithm works, you need to be able to compare it with something classical. And you could compare VQE to many things. You could compare VQE to what we do with, for instance, tensor networks or with cluster methods. There are many classical algorithms you can compare to. I will compare it to variational Monte Carlo. And the reason I'm comparing it to variational Monte Carlo is not because variational Monte Carlo is the state of the art for chemistry, but it's really because variational Monte Carlo is almost the same as VQE. It's really the closest thing to VQE that we have working on classical computer. And so you see when you start comparing this point to point, then things are not so favorable to VQE. Like it's not actually clear at all anymore that VQE has something to bring to the market. And then one cannot discuss quantum computing without discussing the decoherence problem. So I will actually discuss how decoherence actually makes using VQE something real difficult on actual real hardware. And this is really what I mean. In addition to the fact that the classical comparison is very, very difficult to beat, VQE itself would require hardware that is very, very far from what we have at the moment. And so I will stop there for the quantum computing part. And then in the remaining part, I want to still address this accuracy versus precision problem. I want to now to focus on, okay, we identified what is the problem, what we want to solve in chemistry. And I will now turn to the classical techniques. And then my message is actually that the limitation of accuracy right now is not where I thought it was. I thought when I started this business, I thought that the toughest problem, which is clearly the many-body aspect, was really the limitation. And it turns out that when you look at numbers, there is something much more mundane that is limiting the accuracy right now. So I will discuss that. And I will then discuss what we can do with tensor networks to try to address this accuracy limitation. Okay, that's in menu. So let me get started. So yeah, apologize for this slide. It's in French. This is you don't need to understand the French part. It's the point I want to make is actually in the next slide. It's the fact that when you look at the quantum national plans, and I took the French one because I'm in France, but you could do the same thing with any of them, and it would be you would get similar things. So quantum computing has been sold as the solution for many things. But when you look at the specific things that it is supposed to actually to solve, here is actually the list. This is the outline of this French quantum national plan. So it's supposed to do things so that we can actually better health system, feed ourselves better, fight climate change, product better, and so on and so forth. But when you look at these different things and you actually go and see the references, you realize actually that most of these applications have to do with chemistry, with actually being able to solve chemistry on a quantum computer. Essentially, for instance, the fact that we could feel ourselves better is linked to the fact that maybe we could actually learn how to do the catalysis of dissociation of N2 to create ammoniac. That is super important to create fertilizers. And if you can do that, then you can actually fight climate change because you can save a lot of electricity. You can also feed yourself better. I mean, all these things behind, there is always a few papers that correspond to essentially be able to do find better catalytic, better chemical reactions for organic or non-organic chemistry. So it's really the application that has been put forward, I would say, in front of quantum computing. So let me define the problem. The way I will use it today. Essentially, we have a bunch of nuclei, and we want to solve the energy is just the sum of kinetic energy. The attraction by the nuclei, so Zi is actually the charge of the nuclei at position Ri, and the Coulomb repulsion, which makes the entire problem many-body, which make it hard. So this is almost, I mean, of course, you can always add more ingredients. Here I fix the position of the nuclei. You could also add the phonons and so on, but if you can solve that, you can already make huge progress in many fields of chemistry. So the way chemists look at this problem is they first, you cannot, this is in the continuum, you cannot solve any problem in the continuum with a computer. So the first thing they do is to pick up a basis set. So they pick a few orbitals per nuclei, typically, it says a few s and p and maybe d orbitals per nuclei. And then they rewrite this Hamiltonian in the basis that is spanned by these orbitals. So you have a bunch of calculations to do, which I will show in the next page. And then you can actually write this problem in this basis. And once it is done, well, you have a many body problem to solve. It's still super hard, exponentially hard in the number of orbitals, but at least it is finite. And so you essentially need to compute these guys, so the overlap between these orbitals, overlap between the kinetic energy part, and then so essentially use something that looks a lot like the Hamiltonian, except that now these are actually tensors, matrices. You need to do these 6D integrals for getting the Coulomb integral so far, so far. And if you can do that, then you can actually have now a finite problem that you can try and solve. So this is going to be the input of the all the quantum computers, essentially this matrix Hij on this tensor Vijkl. That's the input, and you want to use the quantum computer to get the energy of the ground state, let's say, of the molecule. On the just one remark, these guys are typically of the order of 10 R3. So if you are not used to the R3, it's a unit that chemists like a lot. So it's 27 electron volt. So it's a huge actually energy scale, and so it's 270,000 kelvins. So 2 million for these guys typically. And at the end of the day, you want an accuracy which is of the order of 1 milliard. Why milliard? Because this is more or less 300 Kelvin. And if you want to be able to do to know whether a chemical reaction takes place or not at room temperature, well, you want to know the activation energy, for instance, within something that is comparable to the to room temperature. So you see there are 4 orders of magnitude between the input and the precision that you want on the output. And that's really why chemistry, computational chemistry, is a difficult problem. So now that we have these scales in mind, if you look at, so this, for instance, this is probably the first or one of the first experiments using a quantum computer to actually solve, in this case, it's the energy of H2, so the dihydrogen molecule. So energy versus distance between the two hydrogen nuclei. So you see it, you get a nice minimum. And you see there is the exact curve here, and you have the experiment, which are this black dot. And it looks like the quantum computer is doing something which is quite good, right? It looks very close to perfect. You have to keep in mind that here it's written in a basis where you have actually 4 states. Huh? It's a basis with 2 orbitals. So only 2 qubits are used for solving the quantum problem, which means that you are literally diagonalizing a 4x4 matrix, which you can also do by other means. So it's important to keep that in mind. Now, if you do the same molecule, H2, but instead of taking, so here it was done in a basis which is called STO3G. So the orange one, so this orange here should be the same as this, but it's zoomed a bit more. If you want to use actually a basis which is more correct, it has many more orbitals. Here I took triple zeta. It doesn't matter exactly which one we choose. It's important to realize that so the error you make, so you can consider that this blue one is almost exact. The error you make because you only picked a very, very tiny basis set is of the order of 40 milliard. On 40 milliard, oops, what happened? it's essentially if you it's 1 eV, and 1 eV is essentially twice the sun surface temperature. So even though this looks actually like super good, and even though it is a very small problem, because again it's only used 2 qubits, so 2 to the 2 is actually not a big space. The error that you have here, due to the fact that you use a very small basis set, is actually huge. So it's sufficiently large that is actually not really usable for many means. Definitely much more than the 1 milliard tree threshold that we have decided. That's something that you should always look at when you look at something like some statement about chemistry solved on a quantum computer. Look at the basis set. So this is a precision. The precision is good here, in the sense that you are actually solving the problem that you claim to have solved with correctly. But the accuracy is not good in the sense that the basis set is too small, so it's not describing the reality to the level that you want. Also, keep it in mind when you see statements about making new drugs, for instance. So chemistry is already hard, but if you want to go to biology, if you want to understand drugs behavior for a human being, for instance, well, you already know that when your body temperature change by 1K or 2K, you are not at all in the same state, right? When my body temperature is two degree higher, I'm not functioning, I'm in my bed and I'm ill. So that means that you want to increase the accuracy by at least 2 orders of magnitude if you want to start to be able to do biology. And so all the statements about biology should be taken with a grain of salt. Once again, don't hesitate to stop me anytime. Oh, I see there is a question.
Yes,
Actually, can
exactly,
you?
exactly, Xavier. I wanted to ask you about the bases. You said that the graph to the right is for the two bases. What are these? What's STO3G?
I will come back to that in detail in the second end of the talk. So if I have not answered it by that, you can re-ask
Yeah,
on
thanks.
the. Please don't raise your hand. Just unmute yourself and speak. Just no need to.
Agree.
But the short answer is that these are Gaussians. But okay, I will come to that when I reach the second part. They are supposedly something close to atomic orbitals, like 1s, 2s, 2p, and so on. Except that okay, well, okay, I will come to that later. Okay, this is another example. So in this case, it's a calculation of water. I'm just going to repeat myself here, but you see that here they have 20 milliard tree of precision error. This is actually the data, what experiment with actually on a quantum computer. All the stuff is actually mimicking a quantum computer on using a classical computer. So if you look at this plot, it doesn't look so bad, right? Okay, 20 milliard tree. Okay, we are not yet at chemical accuracy, which is 1 milliard tree, but people could say it's encouraging. It's typically the word that you see. Except that again here, so if you look at the actual energy of water, so this is the calculation that we did, and I will show you a bit at the end of the talk how we do this kind of calculation. But you see that so you extrapolate to m is the number of orbitals, so extrapolate to m equal infinity, you get an energy of the order of -76. On here they have -75. So there is a 1.4 R3 error here on water. So that's 400,000 Kelvin. Huh? Now, so now, once again, you see this, it looks like, oh, it's not so bad, but actually it's extremely bad. And we are talking about water. We are not talking about an enzyme or a cofactor or anything very complex. So that's just to give you where is the state of the art now. And even if you look at this first paper for H2, as soon as you start to look at slightly more complicated problems, so in this case, they look at beryllium H2. So in this case, 1, 2, 3, 4, 6 qubits. You see that, okay, that was some time ago, so now they can do a bit better. But the accuracy that they had was actually much, much, much worse. So already the precision that they had was already not good. Again, accuracy was even worse. And there is this nice paper here that actually looked at, they plotted the number of orbitals that people should have used in order to have actually accuracy as a function of the number of orbitals that actually were used in practice in the experiments. And so in principle, everything should be on the y equal x, because you should use as many as you actually you should need. But you see that everything is very flat here. I mean that people have just used very few orbitals, even though they knew that you needed much more. So that's what I wanted to say about accuracy versus precision, essentially, just to set the stage. Now I'm going to enter a bit how these calculations were performed. So these calculations, like for instance this one, were performed using this virtual quantum eigensolver algorithm. It's a very simple algorithm. So essentially, you start with all qubits in state 0, and you apply a circuit, a quantum circuit. So essentially, you apply a bunch of operations on each qubit and some untangling operations, so some two qubit gates. I assume that everybody knew more or less what this is, but I can give more details if needed. On each of these two qubit gates or one qubit gate is parameterized by some angle, because essentially what we can do in quantum computing is apply rotations along some axis. So each rotation is characterized by a few angles, so typically how much you rotate along which axis. So this gives you a wave function parameterized by some parameters, which are the angles that you put in your circuit. Then you measure all qubits, and you want to estimate the average of the energy. You want to estimate the energy of your ansatz because you want to use a straightforward variational approach. Later, you want to minimize on the values theta until you get the best wave function that you can within this variational ansatz. It's not actually totally trivial because your Hamiltonian will actually have many terms. Just because of the VIJKL, I mean, it's a many-body Hamiltonian, so already it has m to the fourth terms. And actually, you cannot measure the entire things directly. You cannot even measure each of them separately, easily. Because the only thing you can measure with the quantum computers is the average of product of Pauli matrices. So, for instance, you can measure everybody in the z-axis, or this qubit in the z-axis, this qubit along the x-axis, and so on and so forth. That means that you will need to repeat the circuit many times to measure on all different axes so that you get all these terms. And then for each terms, you need to repeat again to accumulate statistics until you have the energy with enough precision. And again, you are limited by a large number law. So the precision that you have increase as in Monte Carlo with 1 over square root of the number of samples. So if you want 4 digits, for instance, which is what I claim you need, well, it's 1 over square root of 10 to the 8. So you need at least 10 million samples. 10 million samples, and then you need to repeat that for all the different element in your Hamiltonian, which is a lot of element. Of course, it scales at the number of with m with the number of orbitals. And then you actually also want to optimize with respect to theta. So you need to calculate the gradient of the energy with respect to theta. And again, you will need to repeat what I just said above now for each of the parameters. You can calculate the gradient. It will essentially change the circuit a little bit. It will when you calculate the gradient. But for each element of the gradient, you need to repeat the calculation. And there may be many degrees of freedom. Typically, in variational Monte Carlo, we use modern variational Monte Carlo. We use tens or 100,000 parameters for if you want to have something which has expressivity large enough to actually describe your real ground state. So you calculate this gradient, and then you update the parameters using some sort of steepest descent. So you actually go in the direction where the energy goes down, and you repeat the same thing until convergence. So this is really the variational quantum eigensolver in very simple version. Right.
Excuse me, so you mentioned number of variational parameters, but this is also related to the accuracy you want to approach, right? So how does it scale with the
This is
accuracy?
largely open because maybe if you are super smart and you find a circuit which actually encodes directly your something which is exactly what you need, the ground state of your molecule, then maybe you can get away with very few. Initially, at the beginning of this field, people were using what is known now as hardware efficient ansatz, and essentially they packed the circuit with as many gates as they could. Because anyway, you know that whenever you do nothing, decoherence is still there. So you might as well add a parameter on the do the best. And it turned out that this is really bad. You get something called barren plateau, which means that your gradient is very flat. And this is something that we start to understand now is due to the fact that most of these states, if you take a random value of theta with a circuit here which has no structure, most of the states will be essentially Porter-Thomas, so random states, if you want. On random state, and then there are a few interesting states hidden in a huge forest of states which have zero structure, which are like chaotic. And your descent cannot find them. So then they stopped doing that, and they started to use ansatz very close to what you do in computational chemistry. So something inspired by the couple clustered method. But of course, when you do that, you need much more the depth of your circuit increase, and it's it's much harder on the hardware. I would say that a good minimum rule of thumb is that if you have m to the fourth entry in your problem, you VIJKL as m to the 4 different component, you need at least as many parameters if you want to be able to solve that. So m to the fourth, I would say, is the bare minimum.
Thank you.
That's what I took for the estimate I will give later. Probably in practice it's more, but at least it's difficult to imagine that you can solve something with that which has m to the fourth parameters with less than that. So this is just a few examples of, we actually did that. We did a VQE of course, we didn't do it on a real quantum computer, we just did it on a laptop. But just to see how the process works so you can see the optimization going so we did it for a few molecules. Okay, just to say that you can do that. It kind of works if you do that on small molecules and you don't put any here we didn't put any noise, we didn't repeat the calculation, we just calculated the average of the ansatz and then did only the optimization. Okay, now as I said, I want to do the same thing, but now the classical counterpart. And the classical counterpart is variational Monte Carlo. So let me introduce variational Monte Carlo quickly. So it's essentially the same thing. Variational Monte Carlo, you have some ansatz that you cook up. And you know how to compute this ansatz for a given configuration, for a given, let's say, configuration being whether this orbital is occupied or not with 1 or 2 electrons, with spin up or spin down. That would be a configuration. So when I was young, we used to spend like a year or two constructing an ansatz, which I call physically inspired. So essentially, you would solve the problem in various limits, and then you would try to construct something that would be correct in these limits, and then interpolate in between them, and that would be the ansatz. Modern way is that don't think, don't do any physics, just take a big neural network and consider that this is your ansatz. And it could be many things actually, this ansatz. Now we are starting to look at things that are intermediate between tensor networks and neural networks, and it's a day that it's really the field that is now booming again. There is a big revival on this field using method adapted for machine learning. So you build your ansatz, then you calculate the energy, and then there is already a big difference with quantum computers. And the difference is that you can actually evaluate the average of the energy directly. Because you know the value of the ansatz. In quantum computers, you can never know any value. You can only sample. But here we know the value of the ansatz, so we can actually calculate this average. And that means that if we find the correct solution, something very close to the eigenstate, to the ground state of H, then the error, which is the variance of the energy divided by the square root of the number of times we actually sample it. But these guys now, the error goes down to 0 when the optimization actually improves the things. And that's a huge difference with respect to quantum computing. Like if you can find the correct ground state, you actually, with one sample, you get the exact energy. That's a huge advantage. A second advantage that you get is that you get the gradient with respect to this parameter theta to all parameters for a single evaluation of the function. And this is known in machine learning as automatic differentiation, or maybe you have heard the name backward propagation algorithm. So we have extremely efficient way to calculate the gradient with respect to all parameters, even if there are hundreds of thousands of them, for the same price as one evaluation. So you gain a lot with respect to quantum computing here. And yeah, and so that's essentially, except for these two differences, the algorithm is essentially the same. You build your ansatz, calculate the energy, calculate the gradient, and do some sort of steepest descent to actually minimize the energy. And that's why I said it's a good thing to compare to compare variation Monte Carlo with respect to VQE, because they are really almost the same thing. And that's actually how people got the idea. If you look at most quantum algorithms those days, except for a few of them, very few of them, a handful, almost all of them are classical algorithms that has been reinterpreted in the context of quantum computing. So unfortunately, I don't have examples of variation Monte Carlo in quantum chemistry. This is something that might come up, but we don't have it yet. So I'm going to show you a model that has nothing to do with chemistry. It's actually a transversalizing model that we are looking at the moment. But I want just to illustrate these 2 points. This is energy versus optimization. And you see, initially, you have a lot of noise. And as you optimize your wave function, the energy goes down, as it should. But also, you see there is some sort of plateau, and the error that you get here is much smaller than the one you had at the beginning. You can also here see it on this plot, which is energy versus the variance of the state. Initially, the variance is huge, and you see huge errors. And as you progress in the simulation, the variance goes down and the energy goes down, but actually also your error bar goes down. So you don't need to have like millions of samples to. Typically, we do everything with 1,000 samples, and 1,000 samples is enough at the beginning, and it's also enough at the end because the variance decreases along the optimization path. And this is a typical. Okay, it's a case where variation Monte Carlo works very well, but I would say even when it doesn't work that well, you maybe miss one digit.
Excuse me. Can you go back to the previous slide? I'm kind of curious on the structure at the lower variance on the right plot. So does it say something about excitations in this model or
probably not? Honestly, this is a plot that I asked my postdoc Mia to give me a year ago before the method really worked. Now it looks simpler. You don't have this second branch if you would look at the data now here. And I think that at that time, depending on how you do the optimization, you could actually get stuck in here. I think we were stuck in a excited state. Yes.
Okay, thank you.
But don't. Yeah, this is just that's all I have, and I didn't want to bother him to give me new ones. But it's so the latest data they look like that. This is just a final one versus this parameter here, which is a transverse field. Energy versus Hx, so it looks like that. You have a reference calculation on the one variation Monte Carlo. What is interesting is that if you zoom around here, you see we have something which is almost perfect, and here we are really working on the last. So we have four digits typically in this kind of calculation. And if you look at one of these points, you see that actually we have more like 5 or 6 digits. And this is really the kind of number of digits that first you get with variation Monte Carlo, and actually that you need if you want to do chemistry. Once again, you need at least 4 digits, but you don't want to be you need at least 4 digits, but 5 would be actually better. So this is typically the kind of thing that you want. But okay, let me get out of this model because it's really not the topic of today. So if I summarize my comparison between VQE and VMC, so if you look at statistical uncertainty, so the fact that you have to repeat to get shots, so in VMC you get it using, for instance, Metropolis. Here you just repeat the same circuit over and over again. The fact that you can measure the energy directly here make it that the variance here goes down as you get close to the ground state, and here it doesn't. So you probably gain here, the classical algorithm probably gain at least a factor 1000 with respect to the quantum algorithm. Same thing with the fact that you have automatic differentiation here. You don't have it here, and you have at least 10,000 parameters for anything which is really relevant. So you lose another factor here with respect to the classical part. So also, I think in this table, I didn't take into account the fact that you can only measure parameters one by one. So you can't get the full energy directly. You have to measure different parameters. That's another 10 to the 3 or 4. I don't know. It depends, of course, of the number of orbitals. But so you see that just by looking at that, it's really not clear why VQE is a good idea. Like it looks like you lose already like 7, 8, 9, 10 orders of magnitude with respect to a perfectly classical technique that works today on your laptop. Not to mention that you could also put thousands of GPUs if it's really you want to boost up the computing power of the VMC approach. It's perfectly parallelizable. There is one part which I didn't discuss yet, and this is what I want to do before I go to the last fraction of the talk. The fact that there is decoherence in quantum computers today and tomorrow too. And I want to essentially quickly have a look at that and look at what would be the precision, I mean, the specification of the quantum computers to be able to do VQE on something actually relevant. Ignoring the fact that it has a very strong competitor in VMC. So here is the thing, it's very simple estimate that we're going to make. So the fidelity F that I'm interested in is essentially, so this is what you want, psi v, the variation ansatz. You want to actually create this on your ansatz. But what you really do is you create some density matrix. It's not exactly this. Whenever you do, you apply one gate, for instance, maybe you overshoot a little bit. It's a bit too long or a bit too short, or the amplitude of the pulse is a bit too large or a bit too short, or just even if you do nothing, there is decoherence. You are getting entangled with some other degrees of freedom that are not in your computational space. So everything you do is with some precision, and so you are creating this density matrix, which is not exactly what you want. So this is the fidelity. So it's essentially the scalar product between what you want and what you really do. So you can rewrite the density matrix as what you want times the fidelity. So it's supposed to be 1 if you do it exactly, plus 1 minus the fidelity times the noisy part of the density matrix. Right? This fidelity is going to decrease exponentially with the number of gates that we apply, just because each gate has a given error. Actually, even when you don't apply a gate, there is also an error. And so what I want to characterize now is what is the epsilon here that you need, the error rate per gate that you need in order to be able to actually run VQE for a meaningful molecule. Typically, this epsilon right now is 0.1%. between 0.1% and 1% on the best hardware. If you take like transmons, for instance, in superconducting hardware, typically this kind of numbers that you have right now. And the question is, what is it that you need? So if you have this density matrix, sorry. If you have this density matrix, you are making an error. And the error essentially is y minus f, the difference between the energy of this noisy part and the energy of your ground state, also of your variational state. So if you put that together, like the fact that it decays exponentially, and the fact that okay, so you make this error, you find that it's just three lines of algebra, that this error rate, and you want to reach chemical accuracy, so this is typically 1 milliard tree. This is the order of the error, and this is number of gates, and you want epsilon to be smaller than this if you have to reach chemical accuracy at the end. So that's as easy as that. So I need to have so this we know what it is, chemical accuracy, 1 milliard tree. Number of gates, we can make the estimate that essentially the one I told Henri earlier. Like let's say that we need at least, at the very least, one parameter per unknown in the Hamiltonian, or input in the Hamiltonian, so m to the fourth. In practice, most of the reasonable ansatz are more m to the sixth or m to the seventh, but okay, let's stick to m to the fourth. And I need an estimate for this noisy error. And this is where actually we get another thing which is not very favorable for quantum computers. So if you have a quantum computer, you have actually two energy spectrum. You have the energy spectrum of the molecule that you are trying to diagonalize. You are trying to find the ground state of this molecule. And I know psi I and EI, the corresponding energy levels. Let's say between E0 and whatever, the maximum value. And you have a second energy spectrum, which is the one of the hardware. And it has nothing to do with this one. It has absolutely nothing to do with this one. So when you create your ansatz, you are trying to create something which is actually made out of low energy. So you want to create essentially to approximate the ground state of your molecule. So it's something which is actually here. It has to be made out of low energy of your targeted ansatz. But the thing that it has nothing to do with the actual. It doesn't know anything about the hardware, right? It's really the target what you are trying to solve. So most likely it will be made out of many highly excited states of the hardware. And so now when you start to look at the noise, at the actual noise processes, and the noise they actually know about the hardware, but they don't know anything about the molecule you are trying to optimize. For instance, you find that relaxation want to bring you close to the ground state of the hardware, may very well bring you to highly excited state of the molecules. So we try to put this qualitative argument into something more substantial. So you can actually work with several noise models, and you can look at this typically error versus number of electrons. And here I divided the error by the number of electrons. And you see that even when you divide by the number of electrons, you see that you get something that actually increases. It increases with the number of electrons, and it also increases when you go from very bad basis set to actually basis set that are big enough to actually be meaningful. So we get an error that now increases quadratically with the number of electrons, which makes sense because if you think about it, the reason that most ansatz, whenever we do VMC, for instance, the energy typically scales as a volume, linearly with the number of electrons or with the number of orbitals. And this is due to the fact that we make sure that we have something which is neutral, almost neutral everywhere. Like you don't want to have charges accumulating in one side of your sample and no charges on the other side. Otherwise, you may pay the price of adding charge on your system, and then it may actually be quadratic. But the noise doesn't know that. It knows only about the hardware, not about the target molecule. So you end up with actually a pretty strong term that actually breaks neutrality. So you essentially end up, the noise is going to create dipole in your molecule, and dipoles are really, really bad energetically. And so you see you get something in the order of tenths of R3. This is typically the error for this noise one. Once again, if you put that into Kelvin, you get central sun kind of temperature. So now you can put everything together. And we did several estimates, but for instance, we did one for benzene. And benzene is interesting because it's more or less at the border of what you can do reliably on classical computers. You see, this is a benchmark that was done recently. I mean, not so recently. And blindly, so I think several different authors use different techniques to calculate benzene in this particular basis set, which correspond to 100 orbitals and 30 electrons. And they are all within 2 milliard tree, 7 techniques within 2 milliard tree, and the ones that are not, we understand why they should not be there. So it's a technique when you actually are able to reach milliard tree precision, not accuracy, and this basis set is actually too small to have the accuracy, with a bunch of techniques. So it's not easy, it's not hard, it's somewhere in between. We know how to do that classically. Now, if for this particular molecule, if you work out the epsilon using the formula I gave you before and the estimate I just gave you, you find that you need 12 digits precision on your quantum computer to be able to do that. That's very, very far from what we have at the moment. Very, very far. So typically, you miss a factor 10 to the 9 at least to be able to do these things, which we can do routinely on a classical computer, on a quantum computer. So I think this is essentially what I wanted to say about this comparison between classical and quantum, on what are the difficulties on this problem of accuracy. So now I will try to stop after 1 hour, so to keep time for questions. So in the real meantime, I will just try to be a bit more positive. Here it was more about saying like, okay, this doesn't work. I'm trying to say a few positive things. And I want to go back at this problem of accuracy and see what we can do with modern tensor network techniques. So that will be the way I will actually start to answer the first question I had on what are these orbitals on this basis set. So once again, when you calculate, when you want to put the problem into a given basis set, you need to compute these integrals. And it looks like, okay, whatever. But if you think about it, for instance, the last one, like this VIGKL, they're called the Coulomb integral. So essentially, integral over R1 and R2 of a product of 4 wave functions. This is actually a tough problem. It's a 6D integral. There are not actually so many techniques that you can use to calculate 6D integrals. It's actually a tough problem. And because of that, chemists have been using for very, very long time just one type of integrals, which are called Gaussian integrals. Essentially, where phi I is essentially a Gaussian centered on the atom, on the nuclei, multiply maybe by a polynomial to take into account the finite orbital moment of the orbital, but essentially a Gaussian. And why a Gaussian? Not because they are particularly good, but because they are analytical formula to calculate these integrals for Gaussians. And so that's what I want to discuss now. Yeah, to motivate a bit, okay, maybe I will discuss this one later. Well, just that you can see, just if you ignore the black part, which is the result that we obtained, these triangles here correspond to energy of, in this case, H2 versus 1 over the number of orbitals for 4 different basis sets that are used by chemists on of increasingly large size. So it's called double, triple, quadruple, and quintuple zeta. Essentially, it corresponds to the number of Gaussians that you use per atom, let's say. It's a bit more complex than that, but more or less it is. And you see that it converges. it converges, but you need actually this last two ones are seldom used in practice because you can use them for H2, but as soon as your molecule is a bit large, these are prohibitive. So you can, most calculation that we'll see actually use double zeta, which is quite far from what you would actually need. So once again, these Gaussians, so they are essentially what I write here. So essentially, sum of a few Gaussians centered around the atom. If you just take the 1s orbital of the hydrogen atom, so it's just exponential minus r divided by the Bohr radius, you see that expanding this as a sum of a few Gaussian is not great, right? There is a cusp close to the nuclei. The cusp has to be there just to because of the 1 over r divergence of the 1 over r potential, so the Coulomb potential of the nuclei. So you need a cusp to compensate for this 1 over r. And there is no way you can get a cusp by adding Gaussians. Or you don't even get the tail correctly because the tail here is, well, it's exponential, and here it's a Gaussian, and even if you add more Gaussians, it's actually not that bad in practice. Chemists have been able to do a lot with these Gaussians, but you can feel that there is a limitation in doing that. Yes, to say a bit more about this, this plot is the error on the total energy that you make as a function of the number of orbitals that you take. So what chemists use in practice correspond to the end of these curves. Double zeta to the end of double zeta, or to the end of triple zeta, or to the end of quadruple zeta, or to the end of 5 zeta. What we did in this plot is we actually from this stuff we actually computed the curve before that. You can do that using something called natural orbitals. And you see that, okay, at some point it converges. For instance, you see that the green and the pink here are the same up to this point, which means that here it is actually the best you can do with 10 orbital. Double zeta would be easier, but the best we can do is here. So there is a lot actually, and this is typically 10 to minus 2. Yes, so it means 10 milliard tree, typically 12, I think. 12 milliard tree is the error that you do at the double zeta level, accuracy error. But you could actually get it down to 1 or 2, so you can gain almost a factor 7 just by picking up the correct basis set. Of course, here we did it after the fact. And so what I want to tell you now is a job that we have been working on to actually try to compute the correct orbital basis without using this Gaussian, essentially trying to get rid of these Gaussians and compute directly the correct basis set to make progress on this accuracy. Okay, so for that I need tensor networks. So let me give you a very, very quick introduction to tensor network. One way I like to use to explain what tensor networks are is to start with this integral. So this is an integral. Okay, very simple integral in 10 dimensions, cosine of 10 times sum of variable squares, some confinement here. This integral, 4 years ago, I had no idea how to calculate it. You cannot use Monte Carlo because I took care here to put this cosine term that oscillates like crazy. So you get a huge sine problem, so Monte Carlo will fail. Low discrepancy sequences will fail for the same reason. Basic quadrature fail because it's 10D. Everything fails, essentially. Now, there is one case where we know how to calculate this integral, and that's when it factorizes. So if it factorizes, we can write it as a product, and then calculating the integral is just you calculate the essentially 1D integrals, make the product at the end, and you get the result. So tensor networks, the way I'm going to discuss them today, is essentially a simple generalization of that. I will write my ansatz F as a product not of functions, but of matrices that depend on X, right? So if I can do that, so now J, big J here is a matrix. If I can do this factorization here, where this is a matrix, not too big a matrix, I hope, then I can do the integral of each matrix. And then at the end of the day, I just have matrix vector multiplication and I get my integral. So this is this is the simplest tensor network that you will write. We noted it like this, and it's an approximation of a big object like that. So whenever you see here a link between two tensors, it means that we are summing over the corresponding index as we do in matrix multiplication. So we have actually okay, there are tons of algorithms for working with tensors, tensor networks. Most famous one is DMRG. The one I just used here is a very important one, is the one that allows you to you give as an input a function, and essentially as the output it gives you the tensor network. So this guy is a matrix product state. And so for this particular integral, if you use so you can actually download this library and use it. It's you have it in C++, Julia, and Python. You will see that you get the actual value of this integral, and it converges very quickly as a function of the number of evaluation. So you can actually, behind the hood, what it does, it's really to put it in this form, and then the calculation is essentially trivial. So this new algorithm, it's called tensor cross interpolation. It was largely invented by a guy named Oseledet, and also Dolgov and Siftunov have been took a part of this thing. Is really a new player in the field of tensor networks, and it's a very important new player. For a long time, we have used tensor network to solve quantum antibody problem. Now we have an algorithm that allows to map pretty much anything onto tensor network, and then we can use all the algorithms that have been designed over the years to actually solve the problem. So essentially, the way I see this, the whole field now, is that you have a huge object. You can think about this as a huge vector. If you can put it in this form as a tensor network, then you have algorithm to do all kinds of things exponentially faster than you would do on this big object, because you will only work on the small object here, the small tensors, to solve the problem. So we have algorithms to solve linear problems, find eigenvalues. This is actually DMRG. Calculate scalar product, calculate sums, like integrals. Also, you can do the fast Fourier transform actually exponentially faster than fast Fourier transform. Integration, I just show you examples on tons of things. You can essentially, if you can put your problem in this framework, on the bond dimension here, there's a number of values that this matrices take here is not too high, then you can solve a lot of problems very, very efficiently. So we wanted to look at whether we could actually do that for orbitals. For that, you need a way to discretize orbitals. On one way, many, but one which is particularly interesting, you have a function f of x. Now x is a continuous variable between 0 and 1. And you're going to write x as sigma 1 over 2 plus sigma 2 over 4 plus sigma 3 over 8, and so on and so forth. So essentially, sigma 1, sigma 2, sigma 3 are bits. So you are discretizing, so you put an exponentially large number of points, so 2 to the n points in between 0 and 1. And you label these points according to how you would write, well, to different scales, essentially. Sigma 1 tells you about large scales, sigma 2 about slightly smaller scales, and sigma n about what happens at very, very tiny scales. So if you do this discretization, you get a big tensor here. And now, if you're lucky, it has actually a lower rank, and then you can start to do computation. So I will we'll probably almost skip the last part of the talk. I want to leave some time for questions. So I will just give you the flavor of what we do next. I will not explain the details. So you can do this on function. So if you take this function, for instance, not particularly interested, you can actually, so this is a function, you can zoom, and you can zoom on the zoom, and you can zoom on this very tiny square. And you see this function has been chosen to have features at all scales. This particular function, you can actually write it using TCI. TCI will find that you can actually store it as a tensor network with only 10 to the 5 numbers to describe the function. While here we put 10 to the 12 pixels, so in each dimension. So it's 10 to the 12 times 10 to the 12. So it's 10 to the 24 pixels. So the compression for some functions, for actually many functions, can be very, very impressive. So I would say there is a chance that we can actually represent a lot of functions in 2D or in 3D or even more. using this representation. It's called quantix representation. And actually, we tried on the orbitals, and it works. So you can essentially, this is a error on with respect to the known energy of the hydrogen atom for the various atomic orbitals. So in this case, for H, we know them exactly. But what we did here is to give these orbitals to TCI, even compute the Laplacian on the 1/r in TCI. So really compute the full thing. As a function of, this is a bond dimension, so essentially this size of these matrices. And you see that we can reach, chemical accuracy would be 10 to the minus 3, so we can get, in this case, 5, 6 digits very easily. And here we are, if we want to go beyond that, we can. It's just that adding more bits to the description. So you can actually describe your orbitals in this using this representation. Actually, in this case, the exact ones, not Gaussians at all. You can actually compute all the Coulomb integrals, all the different integrals that I showed before. These are actually the integrals on the upper line, and the error is the lower line. So you see it's again in the 10 to the minus 6. So I mean, essentially, we checked that you could run the entire program of starting with an orbital and computing these things, and then you actually can work with a much larger set of basis set that originally used in using these Gaussian things. You can do things like this, for instance. Let's say, so in this slide, I just take H2 plus, so 2 nuclei and 1 electron. So you want to solve this problem. So you need to calculate Laplacian of the wave function, then 1/r minus position of the first nuclei, 1/r minus position of the second nuclei. So you can put these guys here, you can give them to tensor cross interpolation. It will give you an MPO, matrix product operator, and then solving this problem belongs to finding the eigenvalue of this matrix. So you want to solve HU equal EU. And that's exactly what the traditional DMRG algorithm does. So we can recycle a lot of algorithms that has been designed for many body physics, but here to solve just a regular 3D Schrödinger equation. And it works. I'm not going to dwell on the details, but we are actually more accurate than the reference that we took. So this 5 zeta basis set, which is already a huge basis set, we can solve stuff much more accurately than that. And you get the entire wave function everywhere. Just to, okay, I'm not going to, or maybe I should. Okay, so we actually also have algorithm now to, so I just showed you that we could compute things if we have the orbitals. Now we are designing algorithm to actually find the best orbitals. So really to calculate the gradient of the energy with respect to these orbitals. So that's something we know how to do now. And you can get this kind of plot. So this is not yet published, but we start from a bad basis set. So in this case, it's a very bad basis set. In this case, this is the best Gaussian one for a given size. And then we optimize actually the orbitals. It's quite interesting that not only you gain, but actually starting from the bad one, we could actually gain more because the bad one was didn't have the cutoff that the Gaussian orbitals had. There is a zoom here. So we could actually get even more precision of the best thing we could do with Gaussians. So this is where we are now, and it's okay. I don't want to dwell much more into this direction, but just to say that a lot of things are happening on this tensor network direction. And to conclude, so essentially I spend a lot of time trying to comparing VQE, understanding how it works, and how what you should compare it to, and essentially where it stands. And my conclusion, it's very unlikely that this algorithm, but we could repeat this for other algorithms as well. I mean, essentially, this conclusion holds for more or less all variational approaches using quantum computers. It's very unlikely that this will actually solve real problems, be an actual solutions in practice. That's the bad news. The good news is that a lot of things are happening on the tensor network side. I discussed today something that had nothing to do with many-body physics. I mean, even though it's part of a many-body problem, but it was just playing with plane functions, 3D function, how to optimize them, how to compute integral with them. A lot of problems actually in this direction that people are also trying to solve on quantum computers can be solved like very efficiently using tensor networks. There are also a lot of things going on tensor networks on the many-body problem itself, but this I didn't address today. So, okay, I already spoke for more than 1 hour. So I will stop there. Thank you a lot for your attention. I hope I was not too fast at the end, and so we have still some time for discussion and question if you guys have any.
Thank you, Xavier, for a wonderful talk and inspiration in the end. So it's still there is some solution to the challenging problem. Yeah, we are open for additional questions, and if I may, I'll start then. You mentioned this Gaussian method for s orbitals, and you said that tensor networks can work with p, d, f orbitals better. But what is the traditional method of sampling these other orbitals? Simply Gaussians is not the way. Could you comment on that? How people are working with other orbitals, how they sample them to calculate these integrals?
So traditionally, they only use Gaussians or linear combination of a few Gaussian. When you see triple zeta, essentially it means that the valence electrons, so the electrons that really matter close to the what I would call the Fermi level, like the LUMO-HOMO point, they use combination of 3 Gaussians for triple zeta. Quadruple zeta would mean 4 Gaussians. Essentially, that's what they use. And if your orbital is a Gaussian, then you have actually exact analytical formula to compute these guys. And so you can actually compute this guy, and then you have a many-body problem, and then you pick up your favorite many-body solver. It could be some sort of variational Monte Carlo. It could be cluster, like a coupled cluster method. For instance, a chemist like a lot coupled cluster, like CCSD, CCSDT, that are very good for molecules that are organic, essentially molecules that are where R3-FOC is already a good starting point. You could use DMRG. A lot of progress has been done recently with DMRG. So there are a bunch of different many-body solvers that you could use. But before you can use any of them, you need to discretize the problem onto one of these basis set. And so they can only do Gaussian. So everybody is using Gaussian, even though they know that it's not so great, that you don't get the cusp, you don't get the, I mean, convergence with respect to number of orbitals is actually pretty slow.
I see. Yeah, one more question regarding your 10-dimensional integral. So you compared the error with respect to exact value. So it means this integral has exact value, well known, right? Or
Actually, no. This one we compare with ourselves. We don't know the exact value.
but what is the reference then?
So we put the value in the paper. So if you but it's converged. So you see here, we look at this is the error. So on here, when you see this plateau here, it means that you just increase the rank of the matrices and the value of the integral does not move anymore. And doesn't move anymore because essentially what you have done is exact, and now you are limited by the fact that you are using, for the blue curve, GK15 means Gauss-Conrad 15, so you use a quadrature with 15 points per direction, so 15 to the power 10 points in total, and you get 4 digits, more or less. So you see, and you're increasing this rank, and you're not in the dark, because you can always take your approximation, your matrix product state, and for any points that you want, you can compare this to the real value, because you can actually call the actual integrand. And when you find that you have 15-digit accuracy on the point that you have used, you see, okay, of course, you could always be unlucky and maybe there is a very tiny peak that you missed, and so on and so forth. Except that here you actually know the function, so you know that there is no such thing. So we believe that the value that we have is the correct one, and I don't know of any other technique that can compute this thing. So here you put 21 points per dimension, you get close to 7 digits. Here you go to 10 and so on and so forth. And so we believe we have this thing with 12 or 13 digits. And I don't know any other way to get it.
I see. Thank you. We have a question from
We also
Gleb.
have benchmarks where we could calculate by analytically and compare, and we know zero. You have actually estimate of zero. That's an important part of the technique.
I see. Thank you. Gleb, please.
Okay, I have maybe a quite general question. It's interesting whether this calculation scheme can be applied to time-dependent problem, to quantum dynamics or not. Meaning calculating the transition probabilities or imaginary part of eigenvalues of corresponding Hamiltonians. And I can suggest that this so in such the case, if it's applicable, then it should looks like quantum control simulation, sort of quantum control simulation, and whether this scheme gives or not some results, either it's stable or not stable, can say something important about quantum control problems, about stability of quantum control, for example. So how could you comment on this?
There is a huge literature of this problem, and I would make two cases. Most of the literature is on the time evolution, let's say after a quench or after something, of many-body wave function. So your wave function now has let's say for instance, it could be the time evolution of a quantum computer after. So you have it has an Hamiltonian, you know it, and you look at the evolution of in time. When you are looking really at many-body wave function, where the different indices correspond to different particles or different sites occupied or not, and these kind of things, you find that entanglement entropy is growing in time. And entanglement entropy is actually, so there is the system is getting more and more and more entangled with time. And entanglement entropy is actually the resource that you use in order to be able to use tensor network. So essentially, tensor network works when the system is not too entangled. So in that sense, this technique works. They are probably the best techniques if you want to do dynamics of a many-body system, but they have a strong limitation. It's not so easy to go to large time. Now it's a field that is moving very fast. There is a paper by Núñez Fernandez, which is like a month old, and they found out, for instance, that okay, entanglement grows, but if you rotate the basis in which you are doing the calculation in real time, you can make it saturate. You can make it not stop growing anymore. So there are many ways to do simulations. And if you are smart, maybe you can find a way which actually make it possible to go to very large time. And these people did. So that was the many-body aspect. Now, if you want to use the same technique to do the dynamics on a Schrödinger equation, let's say now it's like a 3D Schrödinger equation, for instance, after a quench or in presence of a microwave field or anything that you want, then the situation is much easier, and there is no growth of entanglement because it's not the real entanglement anymore. Now you have some sort of notion of entanglement, but essentially, since your function remains a nice function with time, it remains easy to represent with tensor networks. So we have a lot of things in the pipeline now doing simulation in very large time of ordinary Schrödinger equations or a few bosons and stuff like that, many where you can go to essentially unlimited time. So it depends a lot on the problems, and even for a problem, it depends a lot on how you actually frame it.
Okay, it's especially the first part of the answer looks very interesting, meaning that So one should pay attention to the degree of entanglement during the dynamics and
Yes.
check this. So probably the criteria of entanglement can play the role in such
Yes, yeah, I have
cases.
other version of okay, this talk I had a little bit on tensor network, but I have other talks where I spend a lot of time on that. On the yes, entanglement. Essentially, you can do the factorization of writing, something like that as a matrix product state works if this part is not too much entangled with this part, because here the pipe that connects these two, if you have a lot of entanglement, you need this pipe to be big, so you need many different values. The bond dimension is going to grow, and then it's not. I mean, you can always do it on paper, but in practice it becomes impractical. So that's really the core resource. Yeah.
So, may I correctly understand that the key of the problem is that in the case of a strong entanglement, it reshapes the way how you divide your system on the subsystems. Well,
Yes.
being
Yes, for instance, if you don't pick up the right order then you may have a lot of entanglement because you are not putting the bits close to the ones that actually they are talking to. That's one thing. You may be in the wrong basis set. You may not use the right network. For instance, now we are stepping away from these guys and we are starting to use trees or even more complex networks that are more natural for your ansatz. And there are many different ways you could actually get the things to be more manageable. At the end of the day, this guy is an exponentially large object. So when you write it like that, you are compressing it. So you are extracting some structure, some information about this thing that you are taking advantage of to represent it much more compact way. So it's not going to work for any left-hand side, only those that have some structure that you can use.
Yeah, I'm interested in that just because I developed a sort of entanglement criteria which uses matrix elements like substitute and obtain. It's applicable for any density matrices of any dimensionality of open quantum systems. So you can, if you know matrix element, then if I don't know if it's if this criteria is correct, it should be tested experimentally. Okay, but if it works, then you just, if you know matrix element, then or can estimate them somehow to some degree, then and each step of time evolution you can say about whether the system is separable or entangled.
I'm not aware of your criteria. I'm sorry, but people in these communities, they have thought a lot about it, and they have actually designed way to measure entanglement in order to optimize the tensor networks and be more effective about that. So there is a literature on this. So probably maybe you could try and see if there is a connection with your work.
Another interesting aspect is that you say that one way to deal with this problem is to rotate in a proper way. And it looks
entanglement is not at all something that is written in marble forever. There are as many definitions of entanglement as there are physicists. Okay, in some cases it's quite clear there is a converge only to one, but if you have two particles, yes. But as soon as you have many body systems, it may depend. For instance, entanglement in first quantization has nothing to do with entanglement in second quantization. There are different concepts. They scale differently. So it's on depending on it's not a rhetorical question, because depending on the definition, you may design actual algorithms that take advantage of the fact that one is smaller than the other to use a representation that takes advantage of that.
You are saying that you choose definite basis of variables or observables, and then it depends on this. The kind of history a system undergoes depends on the basis you choose.
Basis, but even worse, if you just take a given basis, let's say you look at the Hubbard model, for instance. So so you can think in terms of entanglement like, okay, I have these sites on those sites, and I work in second quantization. So my state is essentially characterized by whether site 1 is occupied or not, site 2 is occupied or not, and so on. And I can, if I think like that, I can define a definition of entanglement between half of the system and that half of the system. But you could also think differently, like I have 20 particles, and I wonder whether the first 10 are entangled with the last 10. And this leads to a particle entanglement. It has nothing to do with the other one. And we have a paper on that, for instance, where we actually did some d-energy in first quantization, and it's very different. Entanglement is different. The way it behaves is different from what you get in second quantization. So yeah, it's a concept which is I mean it's not that simple to I mean it's not that it is difficult, but there is not a single definition that you could use and just say that it's frozen in forever.
For me, it would be interesting your feedback on my paper about.
Don't hesitate to send it to me.
Okay.
You can find my email is super easy to find, and you can just send it, and we'll be happy to have a look.
Okay. Maybe I wanted also to ask about some limitations on that. So you mentioned about the way how people disentangle the system applying proper rotations just for tensor network calculation, and it looks like simultaneous diagonalization. If I meaning are there some speed of rotation limitations in that case, or you can one can do it
it's not my work.
arbitrary?
It's not my work, but well, essentially, what you want to do is during your calculation, you want to compute the entanglement between your different sites, and then you compute some sort of gradient of entanglement and try to see how you would rotate that to keep it small. As far as I know, there is so far they don't have any limitation in terms of speed of rotation. It took them a while to find a way to do this, I mean, properly in a way that is robust. I mean, the idea is very easy to explain, but doing that in practice in a way that actually works in a robust way took them a while. They have examples right now on quantum impurity models like Kondo kind of things. And I know they are expanding into more problems. It's something that has been it has been in the air for a long time. I mean, even actually people doing chemistry are doing that in a routine way. Maybe not as well as not for the time-dependent problem, but if you have if you give a d-energy guy, a modern d-energy guy, an Hamiltonian that is trying to solve using d-energy, is first going to start to do a rotation to minimize entanglement. Nothing to do with time now, just trying to find a basis set which has the least entanglement. Yeah, so it's in the air. I would say it's in the air, and there is more than one group doing this kind of thing.
Okay, thank you very much for your extended answers.
Thank you.
And we have question from Sergei Shevchenko. Yes.
Yeah, you compared calculations on classical computers with gate-based quantum computers. What about using adiabatic ones when we are not interested in the spectrum, but rather, say, in finding the ground state? Are they good? What about quantum annealing, which
Yes.
seems to be particularly convenient?
So quantum annealing, well, actually, that's what. So I have not looked at it in detail yet. but that's what we want to do with this project. This project actually corresponds to quantum annealing. You see, there is exactly what the Hamiltonians people are considering. In particular, here it corresponds to what people do with Rydberg atoms. So we could get the ground state. So actually we could get the ground state with 5 digits. And I went and discussed with the people from the Rydberg atom community. I actually went and discussed with actually the guy that invented this thing. So Antoine Brouwais is in Paris. And we have three digits more than they have. And we can do simulations with tens of thousands of, I can do 10,000 atoms on my laptop, not on using a big cluster or anything. So on plus, if you think about what all this is about, so whenever you do some sort of annealing, quantum annealing, you have Landau-Zener transition, right? So you have Landau-Zener transition, so you have to go slowly with respect to the gap with your excited states. That's what Landau told us. And the thing is that you want at the end of the day to get the ground state of a classical Ising model, which is going to be highly frustrated. Why is it going to be highly frustrated? Because if it is not highly frustrated, then it's super easy to find this ground state classically. And when you are highly frustrated, you actually have a closing of the gap, which is exponential. If you look at spin glass, and this problem has been studied a lot, which means that you need to decrease the speed at which you are doing your annealing exponentially. And this has been discussed a lot. I think Sirac did a few papers, Troyer also, like at the beginning of the D-wave hype. There is absolutely zero theoretical reason why quantum annealing should give up a speed up. None. I'm not aware of any good reason. So people are like, okay, there is no theoretical reason, but maybe in practice it works. But it's a bit weak. I mean, it's actually very weak. And I started to do this calculation, okay, here in the context of these Rydberg atoms. And it turns out that even in practice, we can actually do these things much faster and much better than the hardware. Like they have 2 digits. Right now, they have barely 2 digits. Even D-Wave has barely 2 digits. I have 5. I can do bigger systems than they can do. And I didn't work like crazy and put a team of 1,000 people working on that. That's just one postdoc that did that for 6 months, and even not looking at this problem specifically. So I'm very skeptical. If you look at the statement made by D-Wave, they lied recurrently. They say most of the statements they have are wrong. You will see many papers that are now using so-called hybrid technique, which means that actually they are solving most of the stuff on the GPU, and maybe the quantum annealer is doing something, but you have no idea what. They don't show you. They only show you the result of a global thing. Okay, I don't see it. I don't see quantum annealing as a solution either. It's a different different talk.
Thanks for explaining your skepticism.
So we have one question from chat. So shall I
Again,
read?
about limitations.
Can you read it? Because right
Yes.
now
Do you agree that the limit of miniaturization of classical microelectronics has already been reached? 4 to 5 nanometer technology is used in processors today. Have we really reached the limit of what is possible?
so okay, it's about classical computing, and it's true if you look at what the Taiwanese company, what is called NTN. Okay, I don't have the acronym in mind, but there is the most advanced foundry right now is in Taiwan, and they can actually they can show you nanowires that are 3 nanometer wide, so it's very, very dense. I mean, it's really, you can't really get much better than that in terms of size. Now they are trying to integrate more. Now these things are mostly 2-dimensional. They are trying to see if they could integrate maybe many, stack them together, and so on, go a bit beyond that. But at some point, the density of these things, I agree, will saturate. It has already kind of saturated. Which doesn't mean that classical computing is going to saturate itself. There are many things that are in the pipeline, right? I mean, for a guy like me doing a lot of numerics, most of the time my calculations actually are not bounded by the computing time, but rather by the memory access time. And there's a lot of people that are thinking about in-memory computing. And so there are other routes to actually make progress on the classical side. At some point, the limitation will really become how much power you dissipate. On this also, so a lot of supercomputer centers right now, they don't think in terms of computing power per core or computing power per dollar anymore. They really think in terms of computing power per watt. So they try to dissipate much less than what we dissipate now. For AI, it's urgent because AI is burning electricity at a very fast rate. And there is a lot of room for improvement there because all the microelectronics that we know has not been, at least until 10 years ago, it was not designed to be optimum with respect to energy consumption.
Thank you very much. So I do not see other questions. And since it's not the case, let's thank speaker for a wonderful seminar, including answers for various questions. So we enjoyed it very much. Thank you.
Well, thanks a lot for having me. It was a pleasure to talk to you guys, and don't hesitate to reach out if I mean you want to.
Merci beaucoup.
Merci à vous.
Merci.
Bye bye.
Thanks
Thank
to
you. Au
everyone.
revoir.
So see you on next
Thank
seminar.
you. Bye.
Bye.